Hi everyone, and welcome back, Eduvo students. Today, we're jumping straight into a really important explainer on section 16.3 of your software engineering textbook, and we're talking all about component composition. Now, I want you to think about software integration as solving a massively complex puzzle, but there's a bit of a twist. You see the pieces you're given? They don't always perfectly fit together out of the box. So our main job as software engineers is figuring out exactly how to wire these independent puzzle pieces together to build a robust, functioning system. Okay, let's dive into this and look at our roadmap. We're going to start by covering the absolute basics of component composition. Then we'll look at how we solve incompatibilities using adapters, followed by formalizing our interfaces with the Object Constraint Language, or OCL. After that, we'll discuss the architectural trade-offs you have to make, and finally, we'll wrap up with a rapid-fire master recap of Chapter 16 to get you prepped for exams.
All right, kicking things off with Section 1, the basics of component composition.
So let's define this clearly right up front. In modern software engineering, we basically never build everything from scratch anymore. It's just not practical. Instead, we rely heavily on component composition. This is the process of integrating completely independent software components with each other to create a brand new, larger system, or what we call a composite component. But here's the catch. Because these parts are usually developed totally independently, maybe even by entirely different companies on opposite sides of the world, they don't naturally communicate. So to fix this, engineers have to write what's called glue code. Think of glue code as highly specialized code whose only job is to stick these separate puzzle pieces together securely. Now, according to your textbook, there are three primary ways we actually wire these pieces together. We have sequential composition, hierarchical composition, and additive composition. I really want you to pay close attention to this part, guys, because this is a highly critical focus area for your exams. You literally have to be able to list and explain all three of these types. And this brilliantly illustrates exactly what we're talking about. If you just let your eyes follow the flow here, you can visualize the theory perfectly. You can see how sequential acts like a chain, hierarchical acts like a nested command, and additive acts like a side-by-side bundle. Let's actually break each of these down step by step to really cement the concept. First up, we've got sequential composition. This happens when you create a new component from two existing ones by simply calling them in sequence. So component A executes, it finishes its job, and then it passes its output directly as input to component B. Now, crucially, the components don't call each other directly. Instead, an external program or application controls that flow. You'll very often need to write a little bit of glue code here just to take the output from A, maybe reformat it slightly, and safely hand it over to B so their behavior is perfectly compatible. Next is hierarchical composition. In this setup, component A directly calls component B to do a specific job for it. But for this to actually work smoothly, component B has to provide the exact services that component A requires. In the industry, we call these the provides and requires interfaces. If those match perfectly, great, they plug right in and you don't even need external flow control. But if they don't match exactly, well, you're going to have to step in and write some conversion code.
And third, we have additive composition. This is what occurs when two or more components are essentially bundled together to form a brand new supercomponent. In this scenario, components A and B don't actually call each other at all. Instead, their individual interfaces are grouped together and offered up as one package to the outside world. So just a quick micro recap for your notes. Sequential is one after the other, hierarchical is one directly calling the other, and additive is bundling them side by side into a single unit.
Okay, moving on to section 2, solving incompatibilities with adapters.
So what happens in the real world when you buy two third-party components and their interfaces just completely clash? Well, your textbook outlines three specific types of incompatibility you're going to face. First is parameter incompatibility. This is when operations might have the exact same name, but they expect the wrong data types, or maybe a different number of parameters entirely. The second is operation incompatibility, which is simply when the method names are completely different. And the third is operation incompleteness. This just means one component's provided interface is only a small subset of what the other component actually requires to function.
So, how do we as engineers actually solve this mess? We're going to use the define first rule here. We build an adapter. What is an adapter? It's a highly specific piece of glue code that converts one interface into another to reconcile these mismatched components. It basically acts as a middleman. It takes a request from component A, translates it into a format that component B actually understands, and then hands it over. It's how we force incompatible puzzle pieces to connect safely.
Now, what's really interesting about this slide is how clearly it proves why we need these adapters. Take a look at that component up top, the address finder. Its output is a full location string, but look at the one below it, the mapper. Its displayMap method requires a very specific postcode string, not the whole location. They are totally incompatible. So to fix this, we write an adapter, in this case, a postcode stripper. It takes that full, bulky location from the address finder, strips out just the postcode, and then passes only that specific data safely into the mapper.
Let's look at another really common example from the text involving a data collector and a sensor. Imagine your data collector outputs a super generic command string, like just the word collect. But the sensor component? It has no idea what collect means. It only has a specific hard-coded method called getData. So, an adapter steps in as a proxy here. It catches that generic collect string, parses it, recognizes what the collector is actually trying to do, and translates it on the fly by calling the specific getData method on the sensor. It totally cements the connection.
Which brings us nicely to Section 3, formalizing interfaces with the Object Constraint Language. You know, one of the biggest challenges in component composition is dealing with ambiguity. Relying on informal, natural English documentation is incredibly dangerous because it leaves way too much room for interpretation, and interpretation leads to major system errors. Our formal solution for this is OCL, the Object Constraint Language. OCL lets us define incredibly strict rules for our components. The two absolute most vital terms you need to know here are preconditions and postconditions. A precondition defines exactly what must be true before a method is even allowed to run. A postcondition specifies what the method absolutely guarantees will be true after it finishes execution. Please memorize these two definitions because they are basically guaranteed to show up in your exams. Let's meticulously walk through this snippet of OCL code for a photo library interface so you can see it in action. First, check out the preconditions section. Before you can even attempt to add an item, the library size has to be greater than 0, and the photo ID must not already exist in the system. Now, look down at the postconditions. Do you see that @pre syntax there? It says libsize equals libsize at pre plus 1. This formally enforces the behavior that the value of the library size after the operation must be exactly 1 more than it was before. There is zero ambiguity here. It's just strict, undeniable formal logic. All right, let's look at Section 4, the architectural trade-offs in composition. Whenever we integrate systems as engineers, we are fighting a constant architectural battle. There's no such thing as a perfect system. You always have to sacrifice one property to maximize another, all while trying to maintain the separation of concerns, where every component has one strictly defined job. The most common battle you'll face is adaptability versus performance. Composition A uses many small separate components. Now, this is incredibly adaptable and flexible, but it's noticeably slower because of the communication overhead between all those parts. Composition B, on the other hand, uses fewer, tightly integrated components. That eliminates the overhead, making it lightning fast, but it's extremely rigid and incredibly painful to update later.
Let's move to and see how this builds out in a real-world scenario from your textbook. Looking at the first setup, Composition A clearly separates data collection, data management, and the report generator into 3 pieces. That's super flexible. You could easily swap out the report generator for a new one without ever touching the database. But yes, it's slower. Then look at the second setup, Composition B. It totally bundles data management and reporting into one massive database component. That is much, much faster and great for data integrity, but if your boss suddenly wants to change how reports are generated, you might have to rip out and replace the entire database system.
Which brings us to our final stop, Section 5, the Chapter 16 Master Recap. All right, we are in the home stretch of this explainer. Get those pens ready because this is your rapid-fire exam prep, synthesizing the most critical takeaways from the entire chapter. So the crucial point is knowing your core definitions. First, what is a component? It is an independent, deployable software unit defined strictly by its public interfaces. Second, what are component models? These are simply the agreed-upon standards for how those interfaces are defined, used, and deployed. And third, you have to understand CBSE processes. You must be able to explain the difference between development with reuse, which is assembling a system from existing components, and development for reuse, which is intentionally spending extra time building generic components for other people to use in the future. And please, whatever you do, do not forget the historical case studies. The catastrophic disaster of the Ariane 5 space launcher is the absolute perfect example of the extreme danger of invalid assumptions in reused code. Just because a software component worked flawlessly in an older rocket system absolutely does not magically guarantee it will behave safely in a brand new one.
Rigorous testing and constantly validating your assumptions are non-negotiable, especially when lives are on the line in safety-critical systems.
To wrap up Chapter 16, let's just tie everything back to that original metaphor. Integrating software components is exactly like solving a massive global puzzle where the pieces just don't naturally fit together. And that is exactly why glue code and adapters are a software engineer's absolute best friend. They let us overcome all those crazy incompatibilities, enforce formal behavior using OCL, and carefully manage the constant trade-offs between performance and adaptability. But as these systems get bigger and bigger, and we rely more on third-party code and even AI-generated components, I want you to ask yourself this. How much of the software running our world today is truly understood by the people who stitched it together? It's a wild thought, right? Keep that in mind as you study. Thank you so much for joining me for this explainer, and I will see you in the next lecture.